The next topic is conservation of mechanical energy. Whenever there is some interchange between the potential energy and the kinetic energy, the total mechanical energy, which is the sum of kinetic energy denoted by K and the potential energy denoted by U, remains constant. We can say that K plus U equal to constant, and this is true if there is no frictional forces. In the absence of all sorts of dissipative or retarding forces such as friction, the mechanical energy of a system remains conserved. That means at each and every position the object is in, the sum of kinetic and potential remains a constant. Sometimes we realize that the kinetic energy decreases and the potential energy increases. However, the sum of the kinetic and potential energy will remain unchanged throughout the journey of the object. In some situations, the opposite might happen, where the potential energy decreases and the kinetic energy increases. Still, the mechanical energy remains constant. Say for example, if an object is released from some height above the Earth's surface, if we assume that the air resistance and all other frictional forces are absent, then as the object descends from a specific height, its kinetic energy goes on increasing and potential energy goes on decreasing, but the sum of kinetic and potential energy remains constant. In a similar manner, if an object is thrown up to some specific height, then as the object rises, its kinetic energy decreases but potential energy increases. However, the sum of the kinetic and potential energy remains constant. So let us discuss this property of mechanical energy with respect to a freely falling body. That means a body is released from some height above the Earth's surface, and we will try to calculate the total mechanical energy at some specific points of its journey. So for the time being, we assume a body of mass m is falling freely under gravity. That means it is released from some height h above the ground surface. So with respect to this diagram, I have shown that the object of mass m has been dropped from the point A or the position A. When it is just released or dropped from the point A, its initial velocity u is 0. And if its initial velocity is 0, then definitely its kinetic energy k is also 0, because we already know that kinetic energy is equal to half into mass into square of velocity. Since the initial velocity is 0, obviously kinetic energy is 0. And by the definition of potential energy, that is mgh, the object is kept at some height h above the Earth's surface, and so its potential energy is mgh. Hence, the mechanical energy, the total energy, which has been denoted by E, is equal to k plus u, that is mgh plus 0, that is mgh. Now, let us calculate the mechanical energy at the position B. The object has descended by a distance x, and when it descends, its velocity increases, and let the velocity at the point B be v1. I have assumed that the point B is somewhere in between the point A and the point C on the ground. It is not necessarily halfway between. So I have assumed that the distance is x, and obviously the distance from B to C is h minus x. So at the point B, the kinetic energy is half into mass into square of velocity. The velocity at the point B is, say, v1. So this should be half into v1 square. Now we know that v square is equal to u square plus 2as. This is a very common formula. In this situation, v represents the final velocity. Because the body has descended from the point A to the point B, its final velocity is v1. So I can write v1 square equal to, u represents the initial velocity. The initial velocity was 0, so u square is 0. Because the body is descending under the force of gravity, the acceleration a is replaced by g. So a should be replaced by g, that is the acceleration due to gravity. So it becomes it becomes g. And s is the displacement. So the displacement of the object from the point A to the point B is x. So this is 2gx. So therefore, the kinetic energy becomes half into m. Instead of v square, we will write 2gx, which means that the kinetic energy becomes mgx. Now, the potential energy depends on the height above the earth's surface. So potential energy was mg into h. H represents the height above the earth's surface. In this case, the point B is at height h minus x from the earth's surface. It is at height h minus x from the earth's surface. So this becomes mg into h minus x. So the total energy E is kinetic plus potential, that is equal to mgx plus mg into h minus x. So mgx minus mgx will obviously cancel, and the total energy remains the same as that of the previous case, that is mgh. Please note it down. Okay. So let us now calculate the energy at the point C, that is the point on the ground surface. This represents the ground, that is the earth's surface. When the object reaches the point C on the ground, what is its total energy? So at C, the kinetic energy is half mv square, because we have assumed that as the body reaches the point C, its velocity is v. Now again, by this formula, v square equal to u square plus 2as, here the final velocity is v, the initial velocity is 0. So now I can say that v square equal to, instead of u, the initial velocity was 0, 2as. A represents the acceleration. In this case, a will be g, because the object is falling under gravity. So this will be 2g. S is the descended height, that is total height now, h, because the object has finally reached the point C from the point A, so that the height it has descended is h. So this becomes 2gh. So this is half into m into 2gh, and it becomes mgh. Obviously, as the object has reached the ground surface, its potential energy has become 0, because we already assumed that the potential energy on the earth's surface is 0. So that the total energy E is obviously k plus u. In this case, this is mgh plus 0, which is mgh. So we have realized that the potential energy in all the situations at the point A, at the point B, and at the point C, the total energy remains unchanged, that is mgh at the point C, mgh at the point A, and mgh at the point B. So this is conservation of conservation of mechanical energy of a freely falling body. You can note it down. If you represent this equation graphically, then we can draw a graph between the total energy and the height above the earth's surface. along the y-axis we plot the total energy, the total mechanical energy. Along the x-axis we plot the height above the earth's surface, or height above the ground. When the object is on the ground, its potential energy is zero, and the potential energy linearly increases in this manner. When it reaches the maximum height, its energy completely becomes potential. So at the maximum height, the kinetic energy when it was released was maximum, kinetic energy decreases, and this is what we get. So as per the example that we have taken, this is the point C from which the object reached the point C after falling through height h. This was the point from which the object was released, say for example point A, and this might be somewhere point B. In our example, we considered that B was not exactly in between C and A. For the timing, we can assume that B is halfway through A and C. So if h is the total height, B to C and A to B is h by 2h. So this represents the potential energy graph and this represents the kinetic energy graph. So when the object was at the point A, when it was dropped, its kinetic energy was minimum. As it reached the point C, its kinetic energy went on increasing. When it was at the point A, its potential energy was maximum. The potential energy went on decreasing until the object reached the point C. So this is the graph for potential energy, and this is the graph for kinetic energy. This is the graph for kinetic energy. However, the total energy, that is the total mechanical energy, remains the same, mgh. If you consider that B is halfway between, then in this case, when the object has reached the point B, its energy is half kinetic and half potential. Half mgh will be the kinetic energy and half mgh will be the potential energy. So this we can write as mgh by 2, provided we have assumed that B is exactly halfway between A and C. In the example that we have taken, while we tried to prove the conservation of mechanical energy, we assumed that A to B was x and B to C was h minus x. But in this case, in the graph, we have shown that B is exactly halfway in between. So B represents a height h by 2 of the earth's surface, and A represents a height h of the earth's surface. So the kinetic energy goes on increasing as the object goes from point A to point C, and the potential energy goes on decreasing. So when the object has been released from a specific height, its kinetic energy increases and potential energy decreases, but the sum of the kinetic and potential energy remains constant. In a similar manner, if we project the object from the point C with some velocity until it achieves the height h, its kinetic energy decreases and the potential energy increases. So for a rising body, that means when a body is thrown vertically upwards under gravity, its kinetic energy keeps on decreasing and the potential energy goes on increasing, but the total mechanical energy remains constant. So in both situations, the mechanical energy is conserved. Thus, from this discussion, we can say that the initial kinetic energy provided to the body at the ground so as to reach some height h above the surface must be equal to the potential energy of the body at the height h. This you can note down. The initial kinetic energy that the initial kinetic energy that is provided to the body at the ground so that it reaches the height h above the earth's surface must be equal to the potential energy of the body when it has reached the height h. In this discussion, whenever we have tried to prove the conservation of mechanical energy as well as the corresponding graph, we have already assumed that there are no frictional forces. When the body is descending or falling through, when the body is rising or gaining some height, in both the cases, we are assuming that there are no frictional forces, no resistance, no air resistance, and no such forces which are obstructing the motion of the body. In this context, we can say that the potential energy and the kinetic energy together add up to provide the mechanical energy which remains conserved. So conservation of mechanical energy is a fact which is governed by the absence of any dissipative forces like friction or air resistance. In reality, when an object is falling through some height or when an object is projected to some height, the mechanical energy does not remain conserved because in reality we cannot ignore such forces like friction or air resistance.